This is a pretty cool calculator, right? There's one problem with it. It hasn't got a sine, a cos or a tan button. There's some other problems with it as well, but they're the major problems. I need to know what is sine of 0.5 radians, and this is my only calculator. I'm not willing to use another one. I like this one. It's cool. So how am I going to work out what sine of 0.5 radians is when this is my only calculator? We need this guy. He's called Brooke Taylor, and he's speaking to us from the year 1715. And he says to us, I can't believe you can't do this. I haven't even got a calculator at all. They haven't been invented. And I know what sine of 0.5 is. I'll show you how I do it. Using my magic wand of magic maths, I can tell you that sine x is roughly equal to x. So if you want to know what sine 0.5 is, well, it's roughly 0.5. Will that do? Well, that's very impressive, Brooke Taylor, we say, because we've actually borrowed our friend's calculator, and actually the true value of sine of 0.5 is 0.47942553886. So that's pretty good. It's pretty good, 0.5, but it's not brilliant. I'd like a better approximation to that using my cool Xbox calculator. Okay, fine, says Brooke Taylor. How about this? Sine x is roughly equal to x minus a sixth x cubed. I reckon you can use your Xbox calculator and get a better approximation for sine 0.5 that way. So we get our Xbox calculator and we type in 0.5 times 0.5 times 0.5 because we've got a times button, and then we divide it by 6, and then we do 0.5 minus whatever that is, and that comes out to be 0.47916 recurring. And we say, Brooke Taylor, you are a genius, because the true value of sine of 0.5, according to somebody's calculator that I borrowed, is 0.47942553886, and you've got 479479. That's really good. That's like 3 decimal places. Bang on. That's brilliant, that is. But I want better than that. I want to make it look like I've actually got a proper calculator, even though I'm using my Xbox calculator. So I want like at least 6 or 7 decimal places accurate. Can you do that, Brooke Taylor? I can, he says. I have the magic wand of mathematics. Sine x is don't know why I put that there. Sine x is roughly equal to 1 minus a sixth x cubed plus 1 over 120 x to the 5. Try that, see how you get on, he says. So we put our 0.5 in and we calculate 1 minus a sixth times 0.5 cubed plus 1 over 120, 0.5 to the 5, and we're hoping to get something like the true value of sine of 0.5, which is 0.47942553886. And when we calculate Brooke's idea of using this formula to approximate sine x, what we get is 0.4794270833479424794247942. Excellent. We're agreeing up to 5 decimal places now. Well, actually this rounds to a 3, so 4 decimal places, but it's getting better and better, and it looks to me like Brooke can just keep providing these extra terms on the end here forever. Is that true, Brooke? Yes, it is true. I can literally keep providing them forever, and it will get better and better and better and better. Let's have a look at the graph of these things that Brooke Taylor has been providing us with and see what's going on here. So these are the graphs that Taylor was giving us. First of all, the red one is sine x. That's the true sine x graph. Then the first one that he gave us to start off with was just y equals x. And you can see that actually, given that we're doing sine of 0.5, they're pretty good approximation for that value there. Obviously, if I'd been choosing anything after 0.5, it wouldn't have been very good at all. But for 0.5, that worked out fine. Then the next one, the green one, that was when we demanded a little bit more accuracy, and he gave us y equals x minus a sixth x cubed. So it's a negative cubic, and it's a very specific negative cubic. And look how beautifully, I mean obviously here it's not like sine, but then look, basically from about minus pi by 2 all the way up to pi, this cubic is just basically behaving the same as sine, and then it goes off and does its own thing obviously. And then the next one, the last one that we took, and had a go with. The yellow one, we had y equals x minus a sixth x cubed plus 1 over 120 x to the 5. So this is a positive quintic graph, which goes from down here up, wobbles and joins in with the sine graph much earlier now, almost exactly the same as sine, and then goes off and does its own thing. And this is just beautiful, isn't it? The fact that we can find these polynomials that almost exactly match sine and is just amazing. And that's why when we were sticking in that value of 0.5, the approximations were getting better and better. Wouldn't have worked over here. That's we'll have to think about that later. But that's what's going on. These polynomials are approximating sine, and I'll show you what a really high order one looks like. It's pretty cool. So on this graph you can see lots of different approximations to sine x. The sine x is here in black. That's the sine x graph. And then our first approximation is linear. That's that red straight line. Then the next one we get is a cubic. We don't get a quadratic approximating sine x because it doesn't behave like a quadratic at this point, which is where we're looking, near 0. So we get this cubic coming down like that. That's the orange one. Then next we get this yellow quintic graph. That's to the power of 5, and you can see it does this little wobble here, and then it does another wobble here, and just sits beautifully on top of that sine graph. And then we get this green one coming down, and oh, it's lovely, almost perfect. Just that shape in the middle is exactly like sine. Then we get the blue one. This is, oh, what power are we on now? 7. This is to the power of 7, almost. Look at that, to the power of 9. Starting to pick up that little maximum point there now in the power of 9, and also this little bit here, but then going down, and then this light pink one to the power of 10. So that more terms that we stick on the end, the further away we get our approximation working, the further away from 0, and also the better the approximation is at any of these points that we choose along here. So we don't need a proper calculator anymore, we can use our Xbox calculator. So here it is. With his magic wand of maths, Brooke Taylor has provided us with a way of finding a polynomial, so that's powers of x, that beautifully fits on top of sine x, and it can be as good as we want. If we want to make it better, we just take more terms. Obviously it's best near 0, you can see that from the graph. If we're near 0, it's going to be the best approximation. The further away we go from 0, the worse it is, but if we increase the number of terms, then we can go further and further away from 0 without it being a problem. And this is called a Taylor series, and this is the Taylor series of sine x. And in the next video, I will show you how to find a Taylor series for yourself, so you don't need Taylor and his magic wand to do it for you. I'm also going to show you how to construct a Taylor series which is focused at a different point other than 0. Because say we wanted to work out sine of something like 6, which is near 2 pi, so over here somewhere. If we want sine of 6, well, in order to use this lovely Taylor expansion here, then we're going to have to go up to, I don't even know what power that is, the 7th power or something, so power of, that's 3, 5, 7, maybe this is like power of 9 to get something that's fitting the curve at that point. So what would be better is to move the approximation over onto, say, the point 2 pi, and then we'd only probably need 2 terms, and it would be a really good way of approximating sine of 6. So those are the 2 things I'm going to show you how to do in the next video.